Well, we just talked about coordination, which is bond forming. Now you may think, well, there must be a bond breaking step too. And there is. It's heterolysis. This is where bonds break. So let's look at this in a mechanism. So let's quickly draw up a structure that could have its bond broken. So we'll just go with that. Cyclohexane with an iodine on it. And this could be a good leaving group. Remember, leaving groups are conjugates of strong acids, and HI is a strong acid, so this would qualify as a pretty good leaving group. It's also a large, sterically it's large, and so that can help as well. So let's see here. If we have a heterolysis, these electrons just leave and go on to that iodine. And this is an equilibrium process because, of course, we could have the opposite, where those two charges come back together in a coordination step. But if this is part of a reaction, then going that way would leave us not headed towards the product or a reaction. So sometimes we don't think about that as much. All right, so this has broken that bond, and heterolysis is the exact opposite of coordination. We've just broken a bond. Now, because we've broken a bond, this is often the rate determining step because it takes energy to break a bond, and that's going to make it so that this is a little harder to do. Whereas coordination is generally not the rate determining step because you normally get energy out when we have making a bond, and so it's usually a fast process, especially if it's just a couple of charges coming together. All right, well, let's go back to that aluminum with the acid chloride here, and let's see what could happen next in that species. So I'm going to draw up the product of the coordination step that we had before. And remember, we've got a negative charge, formal charge on the aluminum, and we're going to have a positive formal charge on the chloride, the chlorine right here. Now, this chlorine is not particularly happy having a positive charge on it, so one of the things that could happen is this bond right here between the carbon and the chlorine could break. It's not a super strong bond, especially when this is coordinating with it. So that could break apart, and we're left with, well, let's draw the carbon in this time. Got a positive charge left on that carbon, which is somewhat stabilized by the fact that we've got an electron withdrawing group up here, so it's pulling away some of the electron density anyway, so it's got a positive charge there. Actually, it would be destabilized by that. Stabilized by this because it's feeding an electron density in there. And we'll have our chlorides, aluminum chloride over here. Ion. So this is just what would happen when a bond is broken. And notice that we just have the electrons originating from the bond, going over to the atom. That's because the electrons live in the bond, and that's how we would indicate that this bond right here is broken. Because if the electrons leave, they're what holds things together, and so when that happens, the bond will break between them, and we'll end up with two species like this.